Dear classmates, welcome back to Combinational ATPG. Today we are going to introduce a very important deterministic test pattern generation algorithm, the PODEM algorithm. In this video, we are going to introduce the idea of PODEM and three important PODEM heuristics. Then we will describe the algorithm in detail, and then we will conclude the PODEM algorithm. If you find that the algorithm is very difficult to understand, please don't be frustrated. The algorithm is indeed very difficult because it makes decisions at internal nodes. For this small example circuit, which has 6 internal nodes, so we have 2 to the power of 6 equal to 64 decisions to make. This is a huge decision tree. However, PODEM proposes to make decisions only at primary input. For this circuit, it has only 3 primary inputs. So the decision tree has only 2 to the power of 3 equal to 8 decisions. This is a much smaller decision tree, and therefore PODEM is faster than the D algorithm. The PODEM algorithm was proposed by IBM Dr. Guo in 1981. The full name is Path-Oriented Decision Making. There are 3 important ideas. First, PODEM only allows assignment to primary input. It does not assign internal nodes, so this greatly reduces the search tree. Second, after assignment of primary input, we perform forward implication, so there is no justification needed. What is the reason? Please think about it. We have a question in FFT. Number 3. We flip the last PI assignment when there are 2 failure conditions. Conditions A, the target 4 is not activated. Condition B, there is no propagation path to any output. Let's see an example first. Given this circuit, consider this stuck at 0,4 at gate G1 output. If we want a logic 1 at gate G1 output, we can backtrace to input B and we assign the 1 here. However, we still cannot achieve our objective, so we backtrace again to input A and we assign A to 1. In this way, we generate a D at the gate G1 output. Now we want to propagate D through gate G3. So we need an objective that is a logic 0 at gate G2 output. If we want to achieve this objective, we can backtrace to input C and we assign C to 1, and then we assign input E to 1. In this way, we generate a 0 here so that we can successfully propagate D to gate G3 output. Now we have 2 propagation paths to choose. We can either propagate it through G5 or G6. Let's say we select the upper path. So the objective now is we want a 1 at gate G4's output. And then we backtrace to primary input H equal to 1. If we assign this primary input, we can generate a 1 here, so we propagate B to the circuit output. In this way, we generate the test successfully. During the test generation, we only assign primary input. We don't assign any internal values. Also, there is no justification needed. This is a simple PODEM example. Now let's see the flowchart of the whole PODEM algorithm. Initially, we set an objective. We backtrace to assign one primary input to achieve our objective. Then we perform a forward implication, which is simply a logic simulation. If we have D or D prime reached at the primary output, then we generate the test successfully. Otherwise, if there is still no D or D prime at primary output, we can try to assign more primary inputs. If test is impossible with current assignment, then we will need to check if there is any untried combination of assigned primary input. If so, we need a backtrack. That means we set untried combination of values on the assigned input, and we continue to forward implication. Otherwise, if there is no more choice to backtrack, then the test generation fails. So this is an untestable fault. This is a conceptual flowchart of PODEM. In the last slide, we have several terminology to explain. First, we need to determine an objective. If D or D prime has not appeared at the fault site, then the fault has not been activated. So our objective is to activate the fault. Otherwise, if D and D prime has appeared at the fault site, then our objective is to propagate the fault effect. Given an objective, we need to determine the primary input value. We need to backtrace to choose a primary input. If there is any conflict occur, we need to backtrack. Please note that backtrace and the backtrack are two different concepts. Although they are different in only one letter, but their concepts are totally different. Backtrace means that we go back to a primary input of a certain signal in the netlist. On the contrary, backtrack means that we go back to our last decision in the decision tree. Now it's time for quiz. Please use the PODEM to generate a test pattern for H stuck at 1,4. Please mark your objective and your backtrace. Now please pause the video and give it a try. Have you finished? Our objective is to activate the fault. So the first objective is H equal to 0. We backtrace to input A and assign A to 0. And we generate a 0/1 at signal H. Now we want to propagate it to the primary output K. So our second objective is to make J equal to 0. Then we backtrace to input B, and we have assigned input B to 1. If B is 1, then E is 1, J is 0, and we have a D prime reach at output K, so we generate a test using the PODEM algorithm. During the process, we have 2 objectives and 2 backtraces. Have you got it correctly? Now we will introduce 3 heuristics proposed by the PODEM algorithm. We mentioned earlier in this chapter that ATPG search for a successful pattern in a large decision tree. Because the tree is very large, so we need smart heuristic to speed up. There are 2 types of heuristic. The first type of heuristic help us to prune an impossible subtree as soon as possible. For example, in this search tree, if we can know that the right hand side of the subtree is actually not possible, if we can prune it early, then we can save a lot of search time. The second kind of heuristic help us to find good assignment as soon as possible. For example, if we can know that b equal to 0 is a good assignment, then we can reach to a successful solution earlier. Please note that heuristics are experience-based rules that help us to make correct decisions. However, heuristics do not guarantee to be correct all the time. In the PODEM algorithm, we have 3 questions to be answered, and the PODEM algorithm proposes 3 heuristics to answer this question. Question number 1. What path do we backtrace? Question number 2. What input values do we assign? Question number 3. What path to propagate D or D' to the primary output? We need 3 good heuristics to answer this question. Good heuristics are simple and effective most of the time. So for question number 1, what path do we backtrace? In PODEM, they have proposed a simple heuristic to make this decision. For a decision gate, that means only one input can control gate output to the objective value. For example, suppose that the objective value is a 0 at the AND gate output. This is a decision gate, and the PODEM proposed to choose the easiest gate input to achieve this objective. For example, if A is a primary input, which is the easiest gate input, then we just directly assign A to 0. Then we can achieve this goal. The other kind of gate is the implied gate, which means one gate input cannot control gate output to the objective value. For example, if the objective value is 1 for this AND gate, then PODEM proposes to choose the hardest gate input. What is the reason of doing this? This is because we want to find out if a test exists or not as soon as possible. If we search, for example, input A and found that actually A equal to 1 is not possible, then we know that this objective cannot be achieved. So we can backtrack to another objective. In summary, heuristic number 1 proposes a simple heuristic to make correct backtrace as soon as possible. Here is an example. Suppose that our objective value is C equal to 0. This is a decision gate for this AND gate. So we backtrace to the easiest input, which is V. However, if the objective value is 1, then we would backtrace hard input, which can be either U or Y. So, how do we know C1 is easy and C2 is hard? We can judge that by looking at the level of the signal, or we can use other testability measures such as scope to make this decision. Now it's quiz time again. Given this circuit and the corresponding scope testability measure, please generate a test for H-14. Please do it twice. In the first time, we follow the PODEM heuristic. In the second time, don't follow the PODEM heuristic. Let's see what's the difference. Now please pause your video and give it a try. Have you got it? According to our controllability measure, CC0 here is 1, and the CC of L is 3. Now our objective is H equal to 0. This is a decision gate. Following PODEM's heuristic, if we backtrace to A, we can assign A to 0 and we can generate the test without the problem. However, if we don't follow the heuristic, let's say we choose the hardest input and we would make a decision so that B is 0 and C is 0. In this case, E would be 0 and J would be 1, which would block the propagation. So we would need a backtrack that wastes a lot of time. This small quiz shows that the heuristic really helps us to make smart decisions early. The second question we need to answer is, what values do we assign to achieve the objective? The PODEM algorithm proposes to keep the inversion parity along the backtrace path. Suppose the objective value is 1 and we backtrace along the blue path. We would assign a logic 1 here because this is an even inversion parity and we can assign the same value as the objective value. However, if we backtrace along the green path, we would assign input 0 here because there is an inversion along the path. For odd inversion parity, we would assign an opposite value to the objective value. In summary, heuristic number 2 counts the inversion parity along the backtrace path for primary input assignment. Question number 3. What path do we propagate? There are many possible paths to propagate the D or D prime to primary output. For a successful propagation, all gate output of the chosen path must have X values. This is called an X path in the PODEM algorithm. For this example, in this circuit, if we want to propagate the D prime, we have two X paths, the blue path or the green path. This is not an X path because the values has been determined, so there is no X along the path. If there are more than one X path to choose, PODEM algorithm proposes to choose the shortest X path. For example, the green path is shorter than the blue path, So we would choose this as the D frontier, and we would propagate through this gate. During the PODEM algorithm, if all the X paths disappear, that means we have done something wrong. We will need to backtrack. In summary, heuristic number 3, try to propagate the Four effect along the shortest X path. However, as we mentioned earlier, heuristics are not guaranteed to be correct all the time. This example shows an example with heuristic number 3, but the guess was wrong. Consider the Stochastic 1-4. We perform a backtrace because we have one inversion. So the assigned value B is opposite to our objective value. So we would assign B to 1. The objective was not achieved. So we backtrace to C again. And we assign C to 1. Now the objective has been achieved. So we have a D prime here. Let's now continue to propagate along the X path. There are 2 X paths to propagate. Let's say we select G5. So the objective is A equal to 1, which can propagate the effect through G5. And we also have the output of G1 and the output of G4 during the simulation. Now we have 2 X paths. One X path is G6, G8. The other X path is G8. According to heuristic number 3, we would choose G8 because it's shorter. So now we try to propagate through G8. To do that, we would set the objective to be G6 equal to 1. If we perform a backtrace, we will backtrace to input D. If we assign input D to 0, after the logic simulation, we have 1, 0, and 1, and 1. That means the X path has disappeared. So we made a wrong decision. Now let's clear the figure. Let's backtrack our last decision. We change D to 1. So this would be flipped. G7 would be flipped. G6 would be flipped. Eventually, we have got the correct solution and generate the test. This example shows that heuristic number 3 is not correct all the time. Now let's look at the PODEM algorithms in more detail. The first function we will introduce is the objective function. The objective function picks an objective. There are 2 cases. First, if the 4 has not been activated, then we set an objective to activate the 4. Second, if the 4 has been activated, then we set an objective to propagate the 4 effect. Given a target 4 on net n stochastic V prime value, if the 4 has not been activated, like the figure on the left, the signal of net n is still unknown. Then we simply return the objective as net n, the objective value is v, which is opposite to the stochastic value v prime. Otherwise, the for has been activated like the right hand side. We now want to propagate the for effect D. Let's select a gate G from the D frontier on the shortest X path, and we select an assigned input N of G. So the objective value is to control net N to a non-controlling value. Suppose that V is the non-controlling value of gate G. For example, for an AND gate, the non-controlling value is 1. For the OR gate, the non-controlling value is 0. So we simply return the objective net as N and the objective value V, which is the non-controlling value. The backtrace function translates our objective to an input assignment. This is essentially a depth-first search algorithm which recursively calls itself until it hits a primary input. So the backtrace function goes like this. Suppose N is our objective net, Vs is the objective value. Initially, we assign V equal to Vs, and then we have a loop while N is a gate output. Along the backtrace path, if the gate N is NAND gate, NOR gate, or inverter, then we flip the objective value. This is to keep track of the inversion parity. And then we would determine whether it's an implied gate or decision gate. If it is an implied gate, we would choose the hardest gate input. If it is a decision gate, we would choose the easiest gate input. Then we would recursively call the backtrace function again. The objective net is N and the objective value is V. At the end of this function, we would hit a primary input. Then we simply assign the primary input to value V. Now, here is the whole function of the PODEM algorithm. This is basically a branch and bound search algorithm. Given a fault and the stochastic value V fault, we first check if D or D prime already reached a primary output. If so, the test has been generated successfully. Otherwise, we check whether the test is possible or not. If there is no possible to generate a test, then we return a failure. There are two reasons for this failure. First is that target 4 cannot be activated. The second reason is that X path disappeared. If a test generation is still possible, we call the objective function given the fault and the stochastic value. We would obtain the objective net N and the objective value Vs. Then we backtrace on this objective. We would find a primary input and the value. Then we assign the primary input to the value and run a forward implication. If the test has been generated successfully, then we get the test pattern. Otherwise, we would need a backtrack. Backtrack means that we flip the last assigned PI value. We change it to V prime and run PODEM again. If we generate the test, then we return success. Otherwise, that means PI cannot be either 1 or 0, so we release the primary input as unknown, and we return failure. So we prune this node completely. Now, let's look at the decision tree of PODEM algorithm so that we can understand why it's a branch and bound search algorithm. In the decision tree of PODEM, every decision is a primary input. So let's say initially PI is 1, P2 is 0, P3 is 1, and PI4 is 1. We are now trying this combination. If we found out that there is no test possible, we will flip the last decision, which is PI4 equal to 0. We call this a chronological backtrack. This was first proposed by DPLL for a accessibility problem as early as 1962. Their concept was to flip the last decision that has not been tried. In this example, we are now trying PI4 equal to 0. Please note that we have a check in this node. That means the initial assignment of PI4 equal to 1 has been rejected and the alternative is being tried. Suppose that this branch has shown to be no test possible. Then we need to backtrack since both PI4 has been tried. So this subtree PI3 equal to 1 is completely removed, and we release PI3 to X. In this way, we prune the PI3 equal to 1 subtree. Now we backtrack to PI3 equal to 0, and now we are trying this combination of PI4 equal to 0. Suppose there is again no test. We backtrack to PI4 equal to 1. Unfortunately, if there is still no test, then we will backtrack up to this level and we remove this subtree completely, and we backtrack one level up since both PI3 has been tried. So we remove this PI2 equal to 0 subtree completely, and then we backtrack to other combination. As you can see from this figure, we prune the subtree along the way. So we call this a branch and bound search algorithm. In summary, the PODEM algorithm proposed to assign primary input value, not internal value, so we greatly reduce the search space. During the PODEM algorithm, we perform only forward implication. There is no justification needed, so we save a lot of time. There are 3 heuristics proposed. Heuristic number 1, backtrace the easy or hard input for decision or implied gate, respectively. And it also keeps the path inversion parity for the primary input value to assign. We also propagate the full effect along shortest X path. And the PODEM algorithm is a branch and bound search algorithm. At the end of this chapter, we want to raise some FFT for you to think about. Question number 1. Is PODEM algorithm a complete ATPG algorithm? That means, are we guaranteed to find a test if it exists? Question number 2. Why does PODEM have no justification? Question number 3. We have already shown an example where heuristic number 3 fails. Can you give me some more examples where heuristic number 1 and the number 2 fails? I hope you enjoyed this video. Please think about this interesting FFT. Bye bye.